This video introduces our research to develop computational human phantoms for radiation protection and medical applications at Hanyang University Radiation Engineering Laboratory. First, I would like to briefly introduce the computational human phantom. The computational human phantom is a virtual digital human model used for computer simulations and analysis. This slide shows a voxel-type computational phantom, which is most popular these days. As you can see here, the voxel phantom is composed of a huge number of voxels with their ID numbers. Each ID number represents corresponding organs in human body. For example, these ID numbers in this sliced image represent skin, lungs, heart, bone, and other organs. After placing voxels of all sliced images in 3D space, a computational human model is finally constructed. Computational human phantoms are mainly used in radiation protection and medical applications. For radiation protection applications, computational phantoms can be used to evaluate radiation risk to human body by external or internal exposures, as well as radiation dose reconstruction for nuclear accident such as Fukushima nuclear power plant accident. For medical applications, computational phantoms are used for treatment planning and plan verification in radiation therapy. In addition, they are used in medical imaging research. The first generation computational phantoms represent human body as simple shape geometry such as slab, cylinder, and sphere. The second generation computational phantoms are stylized phantoms of which organs are represented by quadratic equations. Next generation is voxel phantoms constructed from tomographic images of human body. The voxel phantoms can represent more anatomical realism than the previous models. International Commission on Radiological Protection also uses voxel phantoms as ICRP reference phantoms. However, voxel phantoms have limitation to represent organ shapes because organs are represented by voxels with limited size. We can see the skin voxel model has large holes. In order to address voxel phantoms' limitations, we constructed polygonal mesh surface phantoms by converting voxel phantoms to polygonal mesh surfaces, which are widely used in 3D computer graphics. I'm going to explain conversion procedure. The primitive polygonal model is constructed from voxel model using 3D rendering technique. However, the primitive polygonal models has bumpy surfaces because of the remaining of stair-stepped voxel model during the rendering procedure. So, we refined the primitive model by smoothing surfaces, minimizing number of facets, and finally adjusting organ volume to match original mass values. This is the result of converted polygonal mesh model. As you can see, polygonal mesh skin model can represent thin structure of real skin without any holes. Next, we can see the constructed internal organs as polygonal models. As like skin models, wall organs also represent well their thin wall structure without any problems. Small and large intestines, due to their complex shapes, it was impossible to construct polygonal models using the aforementioned methods. Therefore, 3D contouring and NURBS modeling methods were used for them. This is the completed polygonal mesh surface phantom. In contrast with conventional voxel phantoms, it is possible to represent thin or complex organs as like their real structure. Especially, the constructed surface phantom is more meaningful than other surface phantoms in that it can be directly implemented in a Monte Carlo code without use of the conventional voxelization method. In addition, we are converting polygonal mesh surface phantom to tetrahedral mesh geometry for representation of density variation. As you can see, the inner space of polygonal mesh models can be divided into many tetrahedrons without geometric distortion. This is the completed tetrahedron mesh phantom. Its external shape is identical to the original shape of polygonal mesh phantom. At the same time, it is possible to represent density variation by using the structure of the tetrahedron meshes. Furthermore, we are developing a patient-specific 4D tetrahedron mesh phantom for 4D dose calculation. The 4D phantom is constructed based on the 4D CT images of patient, therefore fully representing patient anatomical structure and modeling respiratory organ motion. This video shows 4D dose calculation using the developed 4D phantom in real time. As a matter of fact, this is the first 4D computational phantom which is fully compatible with Monte Carlo simulation. It is expected that the use of this 4D phantom technology will significantly improve the accuracy of radiation therapy. In conclusion, our group are developing advanced type of computational human phantoms such as polygonal mesh surface phantom, tetrahedral mesh phantom, and 4D phantom beyond the current voxel phantom technology. Based on our advanced type phantom developing technology, in the future, we will be able to do real-time 4D Monte Carlo dose calculation while a computational human phantom moves following the movement of the human body.
Gangnam Style.